Good morning. Good morning. I will join in a minute. I mean, I will be ready in a minute. Okay, bye. Hello? Can you hear me well? Okay, very good. I'm ready. Okay, fine. I think we are all discussing in the chat box. We can also speak over the mic. Good morning to all participants. Time is now 10:25. So we will start on time when the organizers initiate the workshop. I understand that due to the Google Meet capacity of permitting only 100 participants, we are also streaming this live in the YouTube. So I hope that the YouTube streaming starts on time and also that your internet connection is very good. I use Airtel for kind information.
Good morning to one and all present here. It is pleasure to introduce today's speaker. Dr. Sundrapandian Vaidyanathan is a senior professor at the Research and Development Center at Tech University, Avadi, Chennai, India. He earned his DSc degree in System Science and Mathematics from Washington University, St. Louis, Missouri, USA in May 1996. His research areas of interest are linear and non-linear control systems, chaos theory, scientific computing, operations research, scientific modeling, and soft computing. He has published 560 scopus, indexed research publications in reputed journals, 3 textbooks on science and engineering, and 12 research monographs published by Springer, Elsewhere, and IGI Global USA. The top 2% scientists in various fields research study by Stanford University, USA in October 2020. He has secured the world 10th rank, all-time global rank in the field artificial intelligence and image processing. And this news was reported by national dailies like the Hindu and the Times of India. In the AD Scientific Index as released at rankings for 2022, yes, India ranked 38, Asian ranked 403, and world ranked 5103 among all scientists in the world. He has delivered several keynote addresses on nonlinear control systems, chaos theory, and scientific computing in IEEE international conferences. He has also conducted several workshops on control systems, data science, and scientific computing using MATLAB and Scilab. He has active research collaborations with scientists from USA, UK, Indonesia, Malaysia, China, Taiwan, Tunisia, Algeria, Egypt, Saudi Arabia, Spain, Morocco, and many countries. I welcome you, sir. Kindly take over the session, sir.
Okay. Thanks for the nice introduction.
Thank you, sir.
Let me share the window. Let's try this. This window. I will make it full. Can you see this all of you, a full screen?
Yes, sir.
There may be a small time delay, so it may take a few seconds to see the full screen. Can you see the PDF file with the title of my talk? I am sharing, so I want to check.
Yes, sir.
You can all see, right? So I can start my talk. Okay. Organizers, if there is any issue, you can message me in the WhatsApp in the mobile, and I will be reading and seeing. If there is any problem, voice break or slides not visible or anything, let me know in the messages. Okay, now I will start. Scientific modeling with engineering applications. Okay, this is all I do. So I'm very happy to share my knowledge with you. In the prescribed time, I will present some interesting material that will make the FDP interesting for all of you, the participants. I welcome the participants who are attending this workshop using the Google Meet link, and also other friends who are watching it in the YouTube live stream. I am actually a part of the organizing committee, as I also work for the Welltech. So I first of all thank the Welltech management, our chairman, our vice chairman, and also our chairperson, managing trustee. They are of great inspiration for me in doing my research in Welltech for the last 14 years. Okay, with this introduction, I will start this talk. Actually, friends, I, as it was mentioned in the introduction about me, I travel a lot for the international conferences. That is how I got to collaborate with these scientists from many countries. And in those conferences, I normally conduct give keynote address and also some MATLAB workshop. So as part of the MATLAB workshop, I was giving some scientific models to give examples for the MATLAB simulation. So that is how this talk emerged over the years, and some of the interesting results I will be sharing with you. Actually, to give you the exact date, when was the last time I gave this talk in India? I gave this talk at an Arts and Sciences College in Coimbatore. It is CMS Arts and Science College. They had a national conference. I presented um, along the same topics, but that talk was delivered in 2015, and now we are in 2022. So 7 years is a lot of time in research. So many developments have come, and I, of course, including my own research. Therefore, I will uh, repeat some of the things I said in that conference, and I'm very glad because the audience was less. It was physically delivered. I'm glad that I'm giving this talk and sharing my results with a lot of people who are attending this FTP. Dear friends, I thank you, for attending this workshop. We had various topics during the last few days, like computing applications, Markov chains, spectral density and results, and yesterday I forgot something about dynamics. And today's talk also related to dynamics. Okay, I will start. This is something, I am tempted to skip this, but at the same time, I like to share some of the awards and honors. The reason is, even though I have got so many awards and honors, I am well recognized in my area in control engineering in foreign countries. People know me very well. But unfortunately, in Tamil Nadu or in the other states, people don't know me. If they, even if you tell them that he is a famous scientist, he has done a lot of results, Indian rank, world rank, and all, they will say we have never heard of him. So I think that is true also. So whereas people in my area know me well, others don't know me well, but it's okay. And also this COVID pandemic days made the travel totally ruled out. At least in the old days, I used to travel to Delhi, Dubai, other places and promote my research. Now my international travel has completely stopped. I only travel to nearby places in Salem, Erode. I think they are the cities I mostly go to give some motivational lectures or science lectures and all. Okay, that's why I'm sharing these results, because people don't know about me, what I have done. This is the first award I got in Delhi. Actually, it's a award announced by one web organization, Careers 360, which is a famous students portal, and they are also promoting research for faculty and Along with the Manipal University, they gave research awards in various disciplines: biology, maths, physics, computer science, and all. Interestingly, I got this award not from maths. Actually, I was nominated in two areas, maths and computer science, and I myself did not know in which field I will be chosen, because I am entitled to one award only. Interestingly, I got this award in the area of computer science, because most of my papers are related to computing, even though I consider myself as a control scientist, which is actually a part of the electrical engineering. Okay, I got this award from the Honorable Minister for HRD, Shri Prakash Javadekar, and the person standing next to him is the AICT chairman. It was very nice experience for me in meeting these great people. Actually, I had dinner together with the AICT chairman after the award function got over. This is the next award I got. This is in the year 2020 or 21. I don't remember. I think it's 2020. In the Stanford University, they published top 2% scientists, and they are many great people in this list. You know, Shyam Sundar, famous man, CNR Rao, of course, from CSIR. Is a famous research scientist in chemistry. I met CNR Rao in that award function held at Delhi also. Shyam Sundar also I met. They are all big people, and I am very privileged and happy to be in this list. Of course, research areas different, and the ranks are different. And I just managed to join this list at the end, 10th rank in the area artificial intelligence and image processing. After this, I got some invitations to collaborate with the foreign scientists in Taiwan, China, and all. I'm partly doing collaboration with the Chinese scientist and partly with the Taiwan scientist also. That's all I want to say. This is the last award slide I want to show. There are many more awards, but I don't want to bore you with my own achievements. But so I promise this is the last award. This is the latest one, 2022. And you can see that if you carefully see this slide, you can see that compared to last 5 years, my rank has improved. In Welltech, I stand as number one. In the India, you know, in the last 5 years, my rank has improved from 89 to 35. So if we have an optimistic thoughts, maybe after next 5 years, I may be in the top 25. You know, I have to work at a very high level, and the research is very competitive. I am optimistic, and hopefully I will be in the top 25 after next 5 years. In Asia, I am currently 403. You can see from the list, from the rank 1283, I have progressed by 800, so which is a good number. But again, Chinese are doing great research. Most of the top ranked people are from China. Of course, Singapore also. China, Singapore, they are doing very well indeed. In my world rank has also improved to 5,105. My goal is to reach within top 4,000 at least. It's very, very challenging, highly difficult task, but I want to see some progress to retain my position in Welltech. If the number drops, then I have to explain to Welltech why my number has dropped. So at least if I secure the rank, I mean, if the numbers don't drop, I will be safe in the current place. But research is very, very competitive. That's what I want to say. Okay, now we get into business. What's the time? Time, oh, sorry. I have taken about 10 minutes in the introduction. Okay. We have, of course, friends, there are lots of areas. About 20 or 25, I am well acquainted with. Due to time limitation, I will be focusing on 6 very interesting areas. Starting from the population biology models that many of you must have studied in your school days. We will go up to, you know, step by step electrical circuits, mechanical systems, weather models, chemical reactors, and finally finance systems. I repeat, there are many more, areas like neural networks, neurology, medicine, for instance, fuzzy logic. They also involve a lot of scientific modeling. I have left out. I have to give a 2 days or 3 days workshop to cover all the topics. Okay, let us start. Is the plan okay? I hope you can hear me well so far. Time is 10:45, so I will explain till 12 o'clock. These 6 models slowly. If you have any important question or anything, I can't see the chat box from this screen because I'm using the full screen. You can ask me using your mic. I hope the organizers permit you, or at the end of the talk also you can feel free to ask me. I will give you some time to ask me questions at the end of this talk. You can note the slide number. If you have a questions, kindly note the slide number and ask me with the slide number. It will save our time. Otherwise, I have to search all the talks. Okay, let us start. This is the basic flowchart of scientific modeling that we all use. The mathematical model involves both the science as well as engineering. Both are important. Actually, these days we don't distinguish between the two. That is the real thing which is done in foreign countries. Unfortunately, in India, we have different degrees, science and engineering is held at a higher position, rank than the science in India. But in foreign countries, they hold the same value. Mathematical model is based on these both the concepts, science and engineering. Naturally, we do experiments to validate, verify the mathematical model. And we further do a lot of mathematical analysis and MATLAB simulation. Without MATLAB simulation, I don't think I could have published many papers. I started like a theoretical mathematician like many of you or some of you. Later on, I started using MATLAB also. Only at the time of writing my thesis, my guide asked me to do simulations. Till then, I was not doing MATLAB at all. Okay, so of course, the computer software, hardware, I will explain all this when we go into results. And finally, we get some results. There is a cycling. It's all, a never-ending process, the research that we do and the results that we get. I very much remember when I first published my research paper, my very first paper. I showed it to my American guide, a famous professor. I am nobody, whatever ranks and honors you can see in this slide in terms of the quality of research. I am really nobody or a very small boy compared to my thesis guide, Dr. Burns, of course, a great mathematician, a great engineer. What a brilliant mind he has. Anyway, when I showed my first paper to him, he asked me, "Are you happy?" What can I say if you ask me such a question? I said, "Yes, sir, I'm very happy." No, sir, I never use sir. He does not like being called sir. So I said, "Yes, Dr. Burns, I'm very happy." "You should not be happy," he said. Then like a typical Indian student, I could not ask him much. So I was just listening. You should not be happy. You should plan to improve your results. Plan to do something more. Plan to do something better. You should not stop feeling happy. So that's what he said. So I remember. Research is always evolving. Even though you might have got some results in some area, you can always improve with some better model or better control or better technique, better analysis and all. Okay, it's an evolving process. This is the summary of my talk with one slide. Okay, we have 6 models I have promised, subject to how time permits. At the same time, I don't want to rush through the talk. I have seen some engineering conferences where the speaker uses 200 slides, and as he or she has prepared the 200 slides, no other way, just to run through the slides, impress all and all that. You have done a lot of research or work. I don't see any need to impress you. I am very happy with what I have done. So So the knowledge comprehension is important. I want you to understand the models. If you understand 4 out of 6 models, I don't mind even skipping the last 2 models, and maybe some other time when we meet, I hope some people may invite me also. So later on we can learn the other models. No issue. So let us start with the population biology models. Are you ready? I am not hearing any response. Is it okay so far? Yes. Can we proceed? Please reply. I think many of you have been muted.
Yes, sir. You can proceed, sir.
Okay, fine. Just to check. Okay. You see, friends, this man started the scientific modeling. He was actually a church father of also doing research. Thomas Malthus, brilliant scientist in the late 18th century, economist and all, he started a very interesting growth model that I will explain. So you should remember this name, Malthus. No need to write down everything I say, but you should remember this in your mind. Names of some great people you should know. If you forget my name, it's okay. But the scientist name you should remember always. Okay, the Malthus model is also called as a linear growth model. Many names are there. I usually call it as a linear growth model. Some people also call it as exponential growth model. If you solve the growth model, named after Reverend Father Thomas Robert Malthus, late 18th century. What Malthus proposed was this. Please listen. Don't look at the slides. Let us assume that the conditions are good for the population growth. We are not in any recession or economy slowdown or anything. Normal conditions. Okay, the world was flourishing in the 18th century. No computers and all. No issue. They were very happy and evolving. Malthus proposed that the population density, if you call P of t as the density of the population at time t, P of t, population density at time t, Malthus proposed that it is directly the growth of the population is directly proportional to the population itself. P dash of t stands for the growth density. Okay, so this is the model. P dash of t, the rate of growth, the density of the growth is directly proportional to P of t. I am considering the growth model, so the proportionality constant denoted by k, I am taking k as positive. For growth, if you take k as negative, you get the decay model. Let us not worry about the decay model. Some intelligent friends may have a question. Sorry, if you consider the population, every day some people are born, so babies are born, people die. So when people die and people are born, you have both birth and death. How do you accommodate it in the model? You see, the answer is very simple. Okay, of course, if some people die, the population drops. If some people are born, population growth. We are considering the net total only. You understand? P of t stands for the net population at each day, including births and deaths. In spite of all that, population is growing. So there is no issue about some deaths and all. Everything is accounted in the model. Malthus actually, in his book 1798, he made a prediction that very soon the world will lead to catastrophe. What he proposed was that population is growing at a geometric rate, resources are growing at the arithmetic rate. I repeat, resources are growing at the arithmetic rate, population is growing at the geometric rate. Therefore, at some time, the population will surpass the resources we have. So the world will have a catastrophe, poverty, riots, everything he warned. But that did not happen. I will explain what happened and all. This is the book. Malthus published this book. I hope you can see the screen. 1798, an essay on the principle of population. In this book, he predicted a doomsday scenario. Doomsday, the world will have a catastrophe. It did not happen. Okay, don't worry. Of course, we are having a normal life only. He wrote the book in 1798. Let us try to understand a little bit more about the Malthus model. Okay, P stands for the population at time t. dp by dt, p dash of t means dp by dt is equal to k times p of t. I don't have time to solve this differential equation. Of course, if I am doing it physically with a lot of time, I can do. We separate the variables. Okay, we separate the variables, integrate on both sides, use the initial condition p of 0 is equal to p naught. A simple calculation gives you that there is a unique solution for this model, which is given by p of t is equal to p naught e power kt for time positive. If you look at the differential equation, we call it a linear growth model. Okay, what you have is a linear growth, k times p of t. It's a linear. And if you look at the solution with the exponential time e power kt, we call it an exponential growth model. A question to all the participants. You get the model like this, okay? How do you check whether the model is correct or wrong? What is the solution to do? Anyone, can any participant answer? We propose some model, we get some solution. How do you check if the model is correct or wrong? What is the next step to be done? Can you answer? Anyone? Hey, please reply. I want this to be interactive. Do you know? If you don't know, please say no. I will give the answer. Any answer from the participants? How do you check if the model is right or wrong? I did not check the organizers. If you are muted, I hope that you can unmute and give answer. Okay, I will proceed. Hey, can you hear me? At least answer that. Okay, fine. You see, the answer is we compare the actual results with the proposed theoretical results. You see, we have proposed a mathematical model. I'm saying, or Malthus is saying, the solutions grow exponentially. We have to validate this model with the actual population census data. Only then we will know whether Malthus model makes sense or wrong. That's what we do. See, I cannot explain all these calculations in detail, but to be brief, we get the data from the American population. In 1790, USA population was 3.9 million. In 1800, after 10 years, the population has grown to 5.3 million. So we take t is equal to 0. That's what I'm doing. T is equal to 0. P naught is equal to 3.9. So, in the model, you can put P naught as 3.9. Okay. So when you take t is equal to 1 unit, where 1 unit stands for 10 years, you have the result for P of 1. Okay, so that's what we do. P1 is equal to 5.3. Using these two results, I can get the value of k. You understand, P naught is 3.9. I have the value on the left hand side, P1. Right hand side, you put t is equal to 1. You have P1 is equal to P naught e power k. You understand, P1 is equal to P naught e power k. You simplify, take log on both sides. You can calculate the value of k. K is equal to ln of P1 by P naught. So a simple result gives you the value of k. Using the value of k, you know P naught, you know the value of k. Each unit of time stands for 10 years. Therefore, we can easily predict the population for P2. What you do is you put, sorry, there is a Small typing mistake I made. I thought this is fine. This is fine. P2 is equal to P naught e power 2k. You substitute the value of k. There is no typing mistake. You get the answer is fine. So how do you find P3? P3 is equal to P naught e power 3k. How do you find P4? P naught e power 4k. You can repeat this. So what we are having is P naught. This is how we started. P1. So when we take t is equal to 2, the actual census data is 7.2 million for USA. Malthus model is 7.3. What do you say, friends? Is it a perfect model? Yes or no? Okay. It is tempted for you to say, it may be very tempting for all of us to say it is a perfect model. It is a very good model. Actually, it is not perfect. You see, in my field, control engineering, we often say we look at the steady state values. What do we mean by steady state values? That is, what we are getting is transient results for a few nearby time values. Transient results may be often misleading. You have to consider more values of time and see how the actual results match with the experimental or real results. So if we calculate like this, P2, P3, P4, P5, P6, P7 and all, you can easily verify this in MATLAB. And I form the table. This is taken from a research paper. So the last line is not showing, but you can see that from the year 1870 onwards till 1860, the results are okay. From 1870 onwards, the results are diverging. The USA population is something Malthus model gives you overestimation. 1910, 92, Malthus model is 154 and all. So the Malthus model is over projecting. That is the bad thing about it. It's not a good model, obviously, because it is giving more than double the projection. In 1920, the actual American population was 106, and the Malthus model is giving nearly double the population. It's not a good model. Okay. And this was the crisis pointed out by Malthus, that the resources are inadequate. The population is growing geometrically, resources are growing arithmetically. There will be a point of food crisis. Yeah. Crisis, okay, typing mistake. A point of food crisis, so catastrophe in the world. It's a bad model, not a good model. Then came another scientist named Verhulst, a French scientist. This Verhulst model is a very, very important model. It is named after Verhulst, his name. So he changed the linear model into a non-linear model. So the right hand side, you have dp by dt is equal to kp into 1 minus p by m. Actually, if you expand, dp by dt is kp, which is the Malthus model, minus kp squared by m. Okay, this p squared is obviously a quadratic so you have to subtract. You see the idea, we are overestimating the population. We have to correct. How do we correct? We correct with the correction term, minus k, the same proportionality constant, p squared divided by m. This m is called p infinity, or the carrying capacity. So I will explain what do we mean by p infinity. We can also calculate it, and some of the calculation I don't want to spend our valuable time. You can separate the variables, even though this is a non-linear ODE. How do we solve a non-linear ODE? We have this method called separating the variables. You can separate the variables, simplify and integrate directly. Once again we separate, and using the properties of partial fractions, okay, using the partial fraction techniques, we can simplify 1 over p times 1 minus p by m. I leave those calculations. I have explained, okay, using the properties of partial fraction expansions, we have this integrate both sides, take exponential on both sides, simplify. You will have a logarithmic terms, okay? You have to take exponential on both sides and simplify. So I have left out some steps. I can do it in person sometime, but not now. What is important is this is the actual exact solution. Take limits as t goes to infinity. What happens? Hey, what happens to the first term on the right hand side? Remember that k is positive, k greater than 0. Therefore, e power minus kt goes to 0. You understand? E power minus kt goes to 0 means the first term vanishes. On the right hand side, within the bracket, the second term goes to 0. What happens is 1 over p of t converges to 1 over m. Okay. If we take limits as t goes to infinity, we see that 1 over pt converges to 1 over m. That means p of t converges to m, carrying capacity. You see, the difference is Malthus proposed that the Malthus model as t goes to infinity, p of t goes to infinity. That is why we have the catastrophe in the world. But in the Verhulst model, the population does not go to infinity. The population ultimately converges to a carrying capacity. There is one slide that I did not include. I'm sorry. There is one slide. Actually, if we do a MATLAB simulations for this model, it will be very interesting to see. Normally, when I give MATLAB workshop, I give these examples to illustrate the carrying capacity. When you do the MATLAB simulation, you will see that P of t converges to M. That also helps you to know the value of M. Okay. This is the comparison chart. You know, this is something we normally do in engineering. How do you know your model is good or not? If you send it to some journals, the journal reviewers will ask you, compare your model with the existing papers in the literature. Even if we show some epsilon improvement, our paper will get published. Therefore, it is often expected how your model performs compared to existing model. Actually, the Verhulst model is showing a very impressive results right from the beginning to 1930. You can see that. Don't look at the second column. Ignore the second column. Look at the USA population with the Verhulst population. Compare the second column with the fourth column. You will see that almost a match, exact match, which is really very, very amazing for me. Actually, friends, I really forgot to mention a magazine named Nature. Okay, Nature is the name. Has done simulations of the world and predicted when will be the carrying capacity reached for the world. The resources that we have will be inadequate. Actually, I don't remember the year exactly. I thought of including a slide, but somehow I got busy. I did not put the slide. I think the year is 2076. Okay, I'm saying it from my memory only. 2076 is the year projected by the scientists that the carrying capacity will be reached. And already, if you read the news carefully, okay, you will see that there is a food insecurity problem in some of the European countries and all. Food is becoming a problem. The world is in a big recession. And dollar compared to dollar, Indian rupee is falling and all. There is a big economic crisis in the world. I can talk more, but then this talk will become an out and out economy talk where I talk about GDP, the growth rate, recession, and all. So I cannot get into details, but understand there is a problem in the world. So Nature magazine says 2076. Now we go to two species population biology models. There are lots of types. Okay, I am considering the competing models. I am considering the predator prey models to be exact. Okay, not competing. I want to say predator-prey models to be exact. Competing models, I will consider at another time. I have written some papers, no big deal. But for this talk, we will take a predator-prey model. I will explain everything. You see, so far we considered a single species. We talked about the Malthus growth model, Verhulst growth model. For humans is only a particular case. Don't take a wrong view. We can also consider the bacteria growth, lions growth, rabbits growth and all. If you consider a single species using the same Verhulst model. Some more models have come. Okay, I cannot talk everything in this talk, but historically, Verhulst model is most important, but other models have also come for population biology. Now we go to two species models. It's called the Lotka-Volterra model. In my view, I find it very, very fascinating, interesting. Actually, I was not so interested in this population biology models. Okay, not into this field, but I am a control engineer by profession. I saw my papers are cited by population biology scientists. They say Sundrapandian's theorem on my name. They are applying my results for this field. Till then, I thought I have done some mathematical research. Non-linear observers is my research area, but seeing the applications of my work in this field. I was working at Trivandrum at that time. I showed it to my director in Trivandrum. He was very, very happy. He said, Sundar, hey, you should give a talk for our students and our research faculty. And I gave a talk on this and also how they have done. I have those talks with me. That is how I got into research in this field, because my research is applied into this field. Okay, Lotka and Volterra discovered this in 1910 and 1926. If you read the last line in this slide, I mentioned Sundrapandian's observer design, which is my name, my doctoral thesis, published into papers on my thesis published in 2000, has been applied for the ecological monitoring for multi-species systems, 4 species, 5 species, and also my results are practical results. Normally, people criticize, hey, what is it that you have done? Your research is all maths. Not for me. Generally, this criticism is made when we publish a PhD thesis. They can't say it on me because scientists have applied my research into ecology and other fields. Okay, friends, now I will explain this in detail because I like these models a lot. This is a system of ordinary differential equations. X of t is the population density of the prey population, like rabbits. Y of t is the population density for the predator, hunting animals, like lions. Look at the differential equations. Look at the first dynamics, which describes the prey density, rabbit's density. X dot is equal to ax minus bxy. Suppose y is equal to 0. Y is equal to 0 means what? No lions. Think of it. Rabbits, when there are no lions, they will grow. How do they grow? X dot is equal to ax. Therefore, we are considering the linear growth model with the proportionality constant A positive. So we are considering the Malthus model for this population biology model. Next, we consider the predator density. Suppose X is 0. When the lions don't have any rabbits, the lions don't eat grass, fruits and all. Of course, I saw one story of a crocodile eating only on rice and all in Kerala. I saw a news that this crocodile passed away. A vegetarian crocodile in Kerala temple, Hindu temple. It's very, very rare, okay. Most of the predators live on non-veg animals, meat. So when x is equal to 0, y dot is equal to minus cy. So we are considering the Malthus decay model. I mentioned that k is positive for growth and k is negative for the decay. So we consider y dot is equal to minus cy decay, where c is positive. Now we revisit the interaction revisit the first dynamics. Think of it carefully, friends. XY, the product, represents the interaction between the prey species and the predator species. When rabbits and lions interact, naturally the rabbit density will decrease. Lions will eat on the rabbits, therefore rabbit density will decrease. This we model by minus bxy. You understand, b is positive, Kolmogorov constant, and xy stands for the interaction. The prey density decreases with the interaction. When the interaction gets more and more, prey density will keep dropping. And on the other way, the interaction helps the growth of the predators. More and more interactions means you have very healthy predators. Just to give a mention, I feel very sorry when I see the lions and tigers in the zoo. I last time saw a Trivandrum zoo. The lions, you can see the bones. Some people may ask, sir, how are the lions in Chennai zoo? I did not go recently. Okay, so but in Mysuru zoo, I saw recently the lions looked healthy. It depends on how you feed the lions and tigers. So anyway, let us not change the topic. So this is the interaction. Now we can find the equilibrium points or the balance points. You set x dot is 0, y dot is 0. You find the equilibrium points, which is very, very useful for the mathematical analysis. To understand the behavior of any system, we have to find the equilibrium points, the rest points, and see what is the stability of the system nearby the equilibrium points. See, if you propose any model, calculate the equilibrium points, do simulation, do bifurcation analysis, do some Lyapunov stability search analysis, you can publish your paper in a top SCI journal. Okay, so what I'm talking is the prelude, some basic preliminaries for what can lead to a top paper. Recently, people also modeled for the COVID pandemic and all. They also used some of the models of this type only. Of course, made into a lot of complexities added, but the basic property was like this only. Okay, this I have done some simulations using Lyapunov stability theory. You can show this result. Every orbit other than the two equilibrium points, these two equilibrium points, if you start from there, you will stay there forever. Except for these two equilibrium points, you can show using Lyapunov stability theory that every orbit is a periodic orbit or a closed orbit. I can prove it, but I don't want to keep this a mathematical talk. Actually, it is possible for me to write a Lyapunov function and show that v dot is 0. And if you plot the level sets or the level trajectories, you get, when you put v is equal to c, take various values of c, you get what is called as level sets. They are the closed orbit. So we have the result. Every orbit other than the equilibrium point is a periodic orbit for the Lotka-Volterra. You see, we start in the first quadrant only. Some guys may ask me, Professor, why do you take the results in the first quadrant? If you do, it's a stupid question. Why? Because we are talking about a real world model where the population density we are talking about. X stands for the rabbit density, Y stands for the lion density. In other words, prey on the x-axis, predator on the y-axis. Therefore, we have to start with positive initial values only. It's stupid to think about x of 0 as minus 12 or y of 0 as minus 15. Therefore, we start in the first quadrant only. When you start in the first quadrant, you see that you have periodic orbits. And there is some point in the center, okay, that is the equilibrium point that I discussed in this model, C by D, E by B. So the center of the concentric closed orbits is the equilibrium point, C by D, A by A positive value. For different values of A, B, C, D, you get different sets of figures. So this is, I don't remember what are the ABCD values. For one set of values, we have this figure. Okay, so this in my view It's a beautiful explanation for the Lotka-Volterra model. Some guys may ask me, sir, can we use the Verhulst model to improve the system? You can do it. It has been published also. So one way of improving this model is, instead of Malthus model, you can think of the Verhulst model to model the X dynamics in the absence of Y. It has been done. I am not doing into those results. We are considering the Malthus model. Lotka-Volterra model is a very famous result. We have done only for the 2 species. We can also do for a 3 species, 4 species and all. As a matter of fact, my latest paper, which is under review, 2022, is about model with 1 prey and 2 predators. See, I cannot give away too many details, but I will say this much. 1 prey, 2 predators, they interact with the prey independently. That is, X2 interacts with the X1, X3 interacts with the X1, and I observed chaos for certain specific values of the Kolmogorov constant. So it is a very important research paper I am doing, a chaotic population model. You don't have portraits like this, okay? It's a very complicated. I cannot share the results with you because it is under review, and the editor says he will contact me soon once he gets all the review results. So in future, I can explain my own results in this population model. Okay, I have finished the first model. I have taken a lot of time. So for the other models, I will take less time. Now we go to second model, electrical circuits. Actually, in the year 1990, I did a course on nonlinear dynamical systems under my guide. Chris Burns is his name. He passed away. I feel sad. I cannot share the awards and the honors I got with my guide. He passed away, unfortunate. He taught me a course on nonlinear dynamical systems. As a part of that course, he taught me some of the circuits, and I got very interested. And that's how I got to do research under my guide. I did my research in nonlinear dynamical systems. So what interested me, I share in this part of the talk. This is a linear model, okay? This is a linear model which is called RLC series circuit. So we have a closed loop, a current flowing, sorry, not a closed loop, a system with an external voltage, a battery V of t. You have everything connected in a series, resistor connected with a capacitor and an inductor, and you have an external battery also connected to the system in a series pattern. Using the standard, the laws that you know from the electrical engineering, you can model this into a integral differential equation. Okay, a very simple calculation. If you calculate the voltage across the inductor is L I dot. The voltage across the capacitor will have integral, and the voltage across the resistor. You know the Ohm's law. Ohm's law says V of t is R into I. Therefore, that you get from Ohm's law, R into I. For L, it is given like L I dot. For C, it is C into integral of I of t. So you have an integral differential equation. Sorry, 1 over C. That Q of t is integral I of t dt. So using the current laws, you have L I dot plus R I of t plus integral I of t dt 1 over C is equal to V of t, the external voltage in the battery. One way of simplifying the system is you differentiate, that is, how do we say, you can replace Q of t. How do you replace Q of t? If you differentiate on that equation, you have Q dot of t is equal to I of t. You know this derivative under the integral sign. Because Q of t is integral I of t dt, Q dot is I of t. Wait, friends, there is something I am worried in this slide. Wait, please. Yeah, that's right. So what is happening is What I said is absolutely right. Q dot is I. Therefore, in place of R I of t, you can put R Q dot. Q double dot is equal to I dot. Okay, Q double dot is I dot. Therefore, you can replace the integral differential equation with a differential equation in Q of t. There is no mistake. This slide is absolutely right. We are replacing I with the Q dot and I dot with Q double dot, okay, which is very easy. So what we have is a second order linear differential equation in Q of t. What are the properties of this and all? I am very much interested in explaining. I postpone. Some of you may be interested in knowing, sir, is it a stable system or unstable? The answer is it is a stable system. Okay, that's all I can say right now. This is a stable system. Stable system means that for a bounded input, you have a bounded output. Suppose the voltage, external voltage is, suppose you take V is equal to 10 volts, a finite value. If you put some constant voltage like a 10 volt to 5 volt and all, Q of t will be bounded. You can easily verify. So it is a stable system. For a bounded input, you have a bounded output. If you take Q of t as the output, it is a stable system. This system is what interested me the most in my I did my master's at IIT Kanpur. Okay, that helped me to do research abroad. I had to do another master's there. So when I was doing that second MS, Master of Science, I studied this. Okay, van der Pol oscillator. It's an electrical circuit. I got scared when I was doing the engineering program. My master's in engineering, I got totally scared. But later on, I developed courage and successfully completed my doctorate in mathematical controlled models. Hey, this is a very, very popular model, a classical model in electrical engineering. One person is unsuitable to be called an electrical engineer if he does not know about van der Pol, because van der Pol has done a lot of research in early radio devices and all in IEEE journals. There are so many special issues dedicated to van der Pol. Okay, let's get into business. Van der Pol was working on a early radio devices. Okay, he was studying sound, a circuit that can produce a radio-like device. And the mathematical model is given by this dynamics. Okay, a second order differential equation. Epsilon, this term is like a nonlinear damping. What you have, the second term, epsilon into 1 minus x square dx by dt is a nonlinear damping. If I put only epsilon, it will be a linear model, a totally useless model. So the nonlinearity which he got with his own research is what makes this model a very valuable model. This is a very valuable model. We have the van der Pol oscillator. To best of my knowledge, we don't have exact solutions of the van der Pol oscillator. It's a very difficult system. I say to best of my knowledge. Some Russian scientists may have actually solved this model. I really don't know, but I say to best of my knowledge only. We don't know the exact solutions. We can do MATLAB simulations and all and plot the van der Pol oscillator. The stability properties of the van der Pol oscillator are very, very well understood. Actually, it is very easy for you to see that the van der Pol oscillator has a unique equilibrium point at the origin. You set x dot is 0, y dot is 0 and solve the differential equations. If you set x dot is 0, you get y is equal to 0. You substitute in the second equation, you get x is 0. Origin is the only equilibrium point that is unstable. This you can verify with the Lyapunov's indirect method. You calculate the Jacobian and you will see the Jacobian matrix as 0, 1 minus x epsilon. That epsilon with a positive sign is contributing to instability of the equilibrium point. It's an unstable equilibrium. So the system is unstable. And this is the phase portrait of the van der Pol oscillator. Dear friends, this is the first example for a limit cycle in the field of dynamical systems. Historically, this is the first appearance of a limit cycle. In terms of bifurcation properties, we say that this is an example of a supercritical half bifurcation. Hey, I had to study this as part of my doctoral thesis. But let us not get into detail, but just those who know, please take it from me that this is a well-known example of a half bifurcation for a system, which involves normally a limit cycle. Mechanical systems, now we go to third model. From now onwards, because of the time limit, I have to wind up by 12. I will be going at a little bit fast. Mechanical system, I wish to go slow, but I need a lot of time. You see, suppose I do a MATLAB workshop at one of your institutions. I can give theoretical lectures for a half a day, in 2 sessions, and we can do MATLAB simulations or Scilab. If you don't have MATLAB license, nothing wrong. We can do a Scilab simulation, which is a free software for plotting these differential equations. Okay, mechanical system. This is something I teach for my aero students. I'm currently teaching a course linear control and non-linear control for the aero students. This model is studied in both of these. If you have a linear damping, we have the linear mass spring damper system. If you can put non-linear damping, we have jump resonance and such properties of the mass spring damper system. Okay, the Ohm's law that you studied is related to something called Hooke's law in mechanical engineering. Ohm's law says the voltage across a resistor is given by R into I. I stands for the current, R stands for the resistor value. Here the Hooke's law says that the displacement is proportional to the spring constant. Therefore, if you call Z of t as a displacement, you can easily calculate there are various restoring force. The restoring force given by the spring is minus k Z of t. The restoring force given by the damper is given by minus b dz by dt. You all know that the damping force is directly proportional to velocity. Therefore, you have two restoring forces, minus k Z of t minus b dz by dt arising due to velocity, and this is the external force pulling the body on the right side. The right side we consider as the positive direction. See, you have to understand, okay, I think you have to visualize. If we pull the body on the right hand side, f of t is measured positive. The force is measured by the Newton's second law of motion. You all know that force is equal to mass into acceleration. So Z of t is the displacement, Z dot is the velocity, Z double dot, d squared Z by dt squared is the acceleration. The positive on the right side. The restoring force will pull the body on the opposite side. Okay, so the restoring force will pull the damper. So that is why they are given in the negative sign, because the spring force, and also that's how you have this. If you use the force balance equation, you have to put with the positive sign and the negative sign. Be careful. So we now go into some of the electrical engineering concepts for those who know the Laplace transforms and all. Hey, no big deal. You take Laplace transforms on both sides, assume zero initial conditions, simplify, group the like terms. You see, in our control engineering, f of t is considered as the input. The external force is the input. What is the output? Z of t, the actual displacement of the body, that is considered as the output. Therefore, we consider the transfer function model, which is the Laplace of the output divided by Laplace of the input. That I denote by f of s divided by Z of s. A simple calculation gives me the transfer function model, which is given by g of s is equal to Laplace of output divided by Laplace of input. This is equal to 1 divided by ms squared plus bs plus k. I said, something about the RLC circuit. Okay, if you do the analysis for the RLC circuit, you have a very similar transfer function. Dear friends, There is a very close analogy between the RLC circuit and the mass spring damper system. This is something every control scientist knows. We have parallels between electrical engineering and the mechanical engineering. If you have an electrical circuit, you can rewrite it as a mechanical system. If you have a mechanical system, you can model it as a series circuit. I mean, I'm talking about the basic models. Complicate models will accordingly translate to complicate electrical models. So in some sense, in a very broad sense of scientific modeling, we can consider the two fields as nearly the same, or they act in a parallel way, electrical energy and mechanical energy, because of the lot of similarities between the two fields. So, the RLC circuit is a stable system. It has a very similar differential equation. This differential equation one, if you compare with the RLC circuit, they are nearly the same. So both of these systems can be easily seen as a stable system. It's a second order polynomial. If you know the Routh stability criterion, the Routh stability criterion says that any second order polynomial is a Hurwitz polynomial if the coefficients are positive. Because the coefficients are all positive, it is a Hurwitz polynomial. It is a stable system. We can also consider this as a state model. Okay, so I have to go fast. This is a second order differential equation. We can either model it as a transfer function model as given here, or as the state model, showing the state model for the differential equation one. The state model is this. Okay, this you can read Raghavendra's book, which is a good book. Raghavendra, of course, my own book. Why you go to Raghavendra's book? I have written a book on differential equations. You can see the same model in my book. We can put it in a matrix form. If you see the matrix form, the matrix A, the eigenvalues of the matrix completely characterize the stability properties. So our friends may be interested in calculating the characteristic polynomial of the matrix A. What are the eigenvalues of A? This characteristic polynomial coincides with the denominator polynomial. Okay, so there is a close relation between the Laplace transform model and the state model. So the characteristic polynomial of that matrix A is given by this equation, ms squared plus bs plus k. If you know the Routh criterion, it's a stable polynomial. It's a Hurwitz polynomial. It's a well-behaved system. So finally, we do some analysis. Okay, this is something we teach students. I remember studying this. I don't know which course. Okay, whether it is physics or maths course, I really don't remember. At least I remember in my masters at IIT Kanpur when I studied this. I remember I studied under a very big man, Professor M.R.M. Rao. He has also written a book on ordinary differential equations. M.R.M. Rao and Ahmad. But I don't know if it is available in Amazon. Read the book. I love that book. Ordinary Differential Equations by M.R.M. Rao and Ahmad. So if you can see in Rao's book or in my own book on differential equations, you have to consider there is, when we have a quadratic, we have delta, delta is equal to b squared minus 4k. We consider three cases of the discriminant. Discriminant delta can be positive. That gives rise to overdamping. Delta is equal to 0. Critical damping. Delta less than 0. Complex conjugate roots. That gives rise to underdamping. So practically, we have these three cases, over damping, critically damping, and under damping. And under damping, you have to be very, very careful because of the external force. There is some danger called resonance. Suppose, you think of a sinusoidal input, a sinusoidal force. In the case of underdamping, the system will have a natural frequency. It is also sinusoidal. When the natural frequency of the system coincides with the external frequency, you have resonance. The system can blow up. This is why the trains, when they cross the bridge, you can see often the train slows down. The train has to, even if it is a Rajdhani or Shatabdi, the train has to slow down due to resonance only. Okay, so this is something I have explained this in my book, okay, I don't have time. So this resonance is something you have to be very careful in the case of underdamped systems. Now we go to, okay, this I am not having time. If we further model a mechanical system, we have a dumping system as a mechanical system with a cubic nonlinearity and a sinusoidal force. I mean, cos or sine does not matter. Okay, a sinusoidal force, you can show that it is a chaotic system. So mechanical system can give rise to chaos. Even the van der Pol oscillator that I showed can give rise to a chaotic system with some external sinusoidal forces. Therefore, we can have a chaotic van der Pol oscillator. We can have a chaotic dumping system, which is a mechanical system. There are a lot of mechanical systems I have studied, like the Rutledge systems, jerk systems, hyperjerk systems, to share a few names. So I have to, these are the mechanical systems which I am happy sharing with you. Please note there are more and more models. We can have a 3-dimensional model, 4-dimensional model. I forgot, I did not forget. I will share shortly. If I do a MATLAB workshop, we can together do these phase portraits, plots using some M files in MATLAB and generate beautiful plots like this. In my view, if you write a paper with some mathematics, some simulations, and some Lyapunov stability analysis, you can publish it in a good Scopus journal. Weather models. Okay, now there are 3 models I am left with. Weather models. I forgot what is the 5th one. I don't remember. Weather models. Last one I remember as the finance models. Finance or fine. Let us say finance. Finance models. In between weather models and finance models, I put some model. I forgot which is it. When we do, we will realize. Anybody remembers what is the 5th model? I think you may not remember. I myself don't remember. I think it's a biology model. Okay, my memory says it is a biology model. I hope 5th is a biology model. Weather models, of course, my talk will be incomplete if I don't mention a very, very famous weather model, which is the, how to say, it is the backbone for my research. Okay, it is. I have ever seen in my research. You see, Lawrence did not get these big awards like what I got, but it should not matter. Okay, I mean, if those days your research is valued by the impact. His research completely made a change on the whole field. So his research is vastly superior to my research. I cannot compare with a big person like Lawrence, but I want to say he's a great man. I did not. I think he passed away. I'm not sure. Weather prediction model. Okay, that is how Lawrence started. Actually, Lawrence got partial differential equations, PDEs. You talk about convection. What is that? Convection. I forgot. Hey, what some of you may remember. Okay, convection, diffusion, and all. Okay, the third thing I don't know. Hey, what is the third one? Convection. Anyone remembers? Convection, diffusion. One more thing is there. 3 types of properties. So considering all the 3, convection, radiation, I don't remember the second one. Lawrence got a set of partial differential equations. He approximated them with the ordinary differential equations. The constants you see, rho, sigma, beta, they are physical constants, real world constants, but they can vary based on the properties of the weather. So Lawrence actually, how he got a chaotic property, I have to take into some other talk, not this talk. He just, by sheer luck, I will simply say, by a stroke of luck, Lawrence got a chaotic system, chaotic properties under these values. And chaotic system and all, I don't want to explain in detail, Some of you are very curious. Sir, what is a chaotic system? Okay, let us answer that question. A chaotic system means it is very, very, very sensitive to initial conditions of the system. It is purely a property of the nonlinear system. Lorentz system is a nonlinear system. It has two nonlinearities. X, Z in the second dynamics, XY. It has two quadratic nonlinearities. For a chaotic system, which is extremely sensitive to initial states, if I start from some initial condition, let us say capital X naught, and you plot the solution corresponding to X naught. You put X naught plus epsilon, where epsilon is a very, very small value. Plot the corresponding solution. If the two solutions are totally different, totally erratic behavior between the two, we call it a nonlinear system, chaotic system. So chaotic system is not bothered whether the system is bounded or unbounded, stable or unstable, no issue. We only measure the sensitivity of the system corresponding to initial conditions. The sensitivity is what I call as Lyapunov exponent. We have to calculate the Lyapunov exponent for the Lorentz system. The Lyapunov exponent value is positive, negative, 0, plus 0, minus. That's why it is a chaotic system with a positive Lyapunov constant. In other words, it is highly sensitive to initial conditions. I have done a three-dimensional phase portrait. We call it a two-scroll attractor because of the two scrolls, or you can even call it a butterfly attractor. Okay, these are some of the names. If any guy saw the movie Dasavataram, Kamal Hassan movie, he mentions about chaos in his movie, and you will see some butterfly flying over the screen, butterfly effect. Actually, the butterfly effect has got nothing to do with butterfly. The Lorentz model, weather predictor attractor, looks like the wings of two wings of a butterfly. As a matter of fact, that movie also deals with the weather, some catastrophe due to some virus outbreak and all. Okay, long before COVID pandemic. Don't worry about all it. We are safe now. This is a 2y xy projection, a two-dimensional projection of a chaotic system, a two-dimensional projection in the YZ plane, and chemical reactors. I'm sorry, actually I thought I will mention biology, neuron model and all. Now I see I have put a chemical reactor on this slide. I will go slow as we have about 15 minutes to complete. See, the Russians have really done some great research in a nuclear reactor. Actually, even the Russia had some nuclear reactors. There was a nuclear explosion in one of the nuclear factory due to poor maintenance. There is one course that engineering students study. Of course, those faculty associated with the engineering departments may know. There is a course called engineering ethics. I taught that course for my control students. We talk about these things. We should run an ethical business and all. There the explosion due to corruption in the management was mentioned. You can have a chaos in the chemical reactor, nuclear reactor and all. I wanted to say it. This is one interesting simple system. Okay, this is not a nuclear reactor and all. Two scientists, chemists, chemical engineers, Williamowski and Rossler. They are Germans. Okay, Rossler, you can see from the name, he is also a famous man like Lorentz. Lorentz was an American scientist. Rossler, a German, 1976. The year of Lorentz system is 1963. After 13 years, Rossler got 1976. He got found a chaotic system from complex chemical reactions. Okay, actually the model has a lot of chemical notation and all. X1, X minus 1, X2 minus 2, X3, X minus 3, the state variables. I have simplified everything. A very complex model, we are considering a very simplified special case with many catalyst value and all set to 0. This is a simplified model. You should ask, is it a nonlinear system? Yes, it is a nonlinear system. I see lot of nonlinearities. 1, 2, 3, 4, 5, 6 nonlinearities in the system. This is a real model, not a cooked up system. Okay, the real systems hold a lot of value. These are some of the phase portraits that you can do to verify the chaos properties in MATLAB. We can do it later, not now. I mean, if we do simulations. I have shown 3 simulations. There is one more model. This is not really a nuclear reactor, but a chemical reactor. There is one model, ZS model. Okay, Zabronsky. I don't know remember this second name. Zabronsky something. Okay, ZS. That is a nuclear reactor model. This is Huang's Chinese. Huang's chemical reactor model 2011. Hawung, I think the right way of calling the name is Hawung. Hawung got a 3-dimensional system with many nonlinearities also. Once again, we see 6 nonlinearities, okay, like the previous Williamowski-Rosler model. Hawung's got 6 nonlinearities, and Hawung found that the chemical reactor model will be having chaotic properties for these values. So this is a 3-dimensional projection. Before I go to the last model, I want to say I have published research improving the results of Hawung. So I published a paper, a 3-dimensional chemical reactor model, a 4-dimensional hyperchaotic chemical reactor model in a Springer book, as a Springer book chapter. So I have done some research related to chaotic van der Pol model, chaotic reactor model. I did not mention, I showed you the van der Pol oscillator in electrical engineering. I found a conservative chaotic van der Pol oscillator model, a conservative chaotic van der Pol oscillator model. Based on these models, I have published many research. So these models have relevance even now. This model is 2011. Don't think it is an old model. It's still a very popular model. Many scientists have worked on the Hawung's system. I am one of those scientists. That's all. Chemical chaotic reactor. Now we go to last model, finance systems. Actually, I like MBA a lot. I mean, the branch, the management studies, I find it to be a very interesting. Just as the science and engineering models are appealing for me, the finance systems are also very, very interesting. But I developed interest in the recent years only. I have published many papers, about 10 papers as I remember. So they are very interesting, lot of important applications, either from the theoretical point of view or from the practical point of view, both. Chinese, once again, are the pioneers of finance systems. These two scientists, Kai and Huang, okay, I like saying this name. I got confused between the two. Hawung chemical reactor and Huang for the finance system. So friends, X is the interest rate in the model. You define a state variable, X interest rate in the model. Y is the investment demand. For any good economy, investment is very, very important. You know, in India, we talk about FDI. What is FDI? Foreign investment, okay, foreign development investment, okay, FDI is very, very important. Sri Lankan economy collapsed because the foreign investments dropped after the COVID pandemic. So the investment is very, very important. Interest rate, I don't know how many of you are following the news. You should read news. RBI recently increased the interest rate. You know, when we saw this news about inflation is growing and all, very recently, just a few weeks ago, RBI increased the interest rate in the savings. Increasing the interest rate will boost the macro economy. Z, price exponent is also very, very important. When prices increase, sales drop. Textile containers went from Bombay to Egypt. The containers were sent back in the ship. Why? The prices were so high. The dollar exchange has impacted the economy totally. The Egypt people did not have the money to buy the textile containers sent from Mumbai to Egypt. The Dean of Management shared this news for me. That's how I came to know. So the price exponent also plays a big role in economy. Interest rate plays a role. Investment demand plays a big role. Price also plays a role. Based on this, we can build a Kai Huang nonlinear finance model, and they have done a lot of research. And by actual analysis, they found that for these, some of you may ask, Professor, how do you get these values? Lot of simulations. Day and night I worked. Of course, I got lucky. That's another thing. For sometimes day and night I worked for generating a new chaotic system. We have to be very, very careful not to duplicate a result. Okay, suppose you publish a paper in a result published by somebody else, he can sue you with an intellectual property law for $1 billion or $1 million. Research, it's like a minefield. You have to be careful. You should publish good papers, but you should make sure that it's previously not done by any scientist. Okay, for me that is a big challenge. I should not repeat my own result also. I will be in trouble even in that case. So we have to make sure we got really a new result. Okay, so the finance system that I described with the three states, interest rate, investment demand, and price exponent, modeled by Kai and Huang, Chinese finance scientists. I call them scientists only. They found that it is a chaotic system. They published in a good SCI journal, very popular system. So these are some of the Facebook rights. Also, I have also done some results. You see, this is a basic model. I have built some. Throughout this talk, I have decided not to put my research in any slide. Okay, the purpose of this talk is to mention famous work done by others, not by myself. So I don't want to put my systems into the talk. It is very tempting for me to think of, a set of talks. First talk on the basic model, second talk with what I have done. But that will have to go to like part 1, part 2, part 3, simulations and all. So I can give only a basic outline for this talk. I come to the end of the talk. I have to sum up quickly. I did not put that, so I will briefly summarize. You see, friends, in this talk, I considered population biology models. We started with, I showed RLC circuit, electrical circuits, mechanical system, the mass spring damper system, a classical system. Also, I showed you the Duffing system in a hurry, Lorentz system for the weather models. I recently published a paper on ocean dynamics, the temperature of our near a ocean. So that can be also a good research temperature model, weather model, chemical reactors. I showed you Rosler system, also Howung's system, finance system, Kai Huang finance system with interest rate, investment demand, and the price exponent as the three states. Now to conclude this talk, okay, I want to show you something and then I will stop. If you have questions, then ask me. This is the first book I published, Numerical Linear Algebra. It is a textbook in NIT Warangal and also NIT Calicut for MSc courses on numerical linear algebra, advanced matrix computations and all. It is a very good book. This is a book which is prescribed for BTech program. The ECE students study probability statistics queuing theory in one of their courses called random processes. Okay. So for the BTech students, I wrote this book. Also, others can read this book. I also talk about, there was a talk about Markov chains given by Nagarajan. I described Markov chains in detail in queuing theory. I have described a lot of examples of Markov chains. What are the steady state properties and all? You can read this book. Lastly, this is a good book that I published. This is also a textbook in many universities. Ordinary and partial differential equations, published by McGraw-Hill, Delhi. You can buy this book. All the models I talked about are given in this book. Suppose you ask, of course, not the nonlinear models, but many of the models. Many of the basic models that I mentioned, a mass spring damper system, 3 cases of damping, they are all given in this book in detail with MATLAB simulations. I mentioned in the cover of the book MATLAB examples. Lastly, this is those who want to know a little bit more about the chaos modeling or the control systems design. You can read my book. The very famous engineer is holding a high post in IEEE. My number one research collaborator, Professor Ahmad Tagar Azar from Egypt. And I published the Springer book. That's all, friends. I'm very keen on finishing on time. I want to thank you for listening to this talk patiently and attending this talk. I will stop sharing. If you have any questions, I will answer orally. We are back to the main screen. We can have a few questions. If any audience like to ask, feel free to ask. Anyone, any questions, feedback? I hope I shared some interesting results. Okay. Any questions, friends? In the chat window, I see 98 commands. I see any question? No, that's people. Okay. In chat command, any question? No questions. So I will say thank you all. I am very interested in conducting a MATLAB workshop or a Scilab workshop. If these models interest you, we can plan in future at your institute. If you call me, subject to my time availability, we can plan a 2 days workshop or a 1 day workshop and discuss these. Ideally a 2-day workshop, because I will need to explain the theory. We can plan a 2 days workshop subject to my time availability and also the budget. That's all I want to say. One question. Okay, open queue. Where is it? Some question. Okay, feel free to ask. Okay, one question. Somebody raised a hand. Please ask. Please ask your query.
Sir, good afternoon, sir.
Yeah, please.
This is Mahesh Kumar from Sri Krishna College of Technology, sir.
Okay.
Sir, I have one question about modeling.
Okay.
When we create a model, mathematical model, we are usually using Routh criterion concept, right, sir?
For checking stability, yes. For checking stability, we use the Routh-Hurwitz criterion.
Is there any
That is
advanced
to analyze. That is to analyze the model, not for building the model. For analysis of the model, we use Routh-Hurwitz criterion.
Right, sir. Correct, sir. Sir, is there any advanced model advanced techniques available, sir?
Sure. Definitely, 100%. You see, the Routh-Hurwitz criterion is actually useless. I will explain. For a linear system, okay, I repeat, for a linear system, you write the characteristic polynomial, okay? The characteristic polynomial, whether the characteristic polynomial is stable, unstable, how many roots are there on the positive side of the complex plane, how many roots are there in the negative side of the complex plane, we call like unstable roots and stable roots.
Yes,
The Routh-Hurwitz criterion gives you all these properties for the linear system only. The many of the models I mentioned, like the van der Pol oscillator, the Duffing equation, what more? The Lorentz model, the Huang's finance system, Huang's chemical reactor model, they are all nonlinear systems. For those systems, Routh-Hurwitz criterion gives you zero information. It's useless. So a good question for you to ask is, or how do we check the properties of these systems? Okay, so First thing is simulation. We do MATLAB simulation. The simulation gives us some property. Based on the simulation itself, you can say the system is stable or unstable. And please note that I
Yes,
can't
sir.
say the wait. I have to correct. Okay, I can't say that the linear system is totally useless, because the stability of the equilibrium for many of the systems I mentioned myself, the van der Pol oscillator, if you use the Routh-Hurwitz criterion I mentioned in my talk, you have the plus epsilon that gives you that the equilibrium at the origin is unstable. So you do get some information using the Routh-Hurwitz criterion. I want to correct myself. Stability of the equilibrium in many of the cases you can consider and conclude. But for checking the system is chaotic or not chaotic, what are the special properties, we have to use something called a bifurcation analysis. Okay, for that we do something more than the Routh-Hurwitz criterion. We do something called a bifurcation analysis, and there is something called a Poincare map. Okay, Poincare map, bifurcation analysis. These things we do. These are the advanced tools. I correct myself. The Routh-Hurwitz criterion is useful to some extent only. I use it all the time. So I am not discouraging from you. I use it all the time, but to some extent only. You have to do something more. Okay. Others, any other question? Yeah, please. Okay,
Thank you,
ask
sir.
me. Yeah. Any other question? You see, friends,
No, sir.
what
No,
I
sir.
want to say is, for any system, nonlinear system, we write the linear parts, nonlinear parts. First, you study the linear part. So, in the first part of the analysis, we do Routh-Hurwitz criterion. I do it all the time. This is the first part only. Then, for the second part, the nonlinear terms also play a role. So, we consider Lyapunov, some suitable Lyapunov function, or bifurcation analysis, or Poincare map. So the first you ignore the nonlinear terms and study. Then we take into account the nonlinear terms. For the Huang's financial model, the interaction play a big role. I mentioned the Lotka-Volterra population models. The interaction terms xy minus xy, they hold high importance. We cannot ignore them. That is what I wanted to say. Okay, please ask others. Others may ask. Yes. 12:05, we can have a few more questions. If no more questions, we can stop. You can contact me by email. Okay, you are welcome to contact me by email, and I can help those who are interested for the things. My mobile number and emails with the organizers. You can contact me in future for any queries. That's all. Okay. The organizers, I leave the session to organizers now. They may conclude.
The finally vote of thank you.
Okay.
Good morning to all. I would like to thank everyone for your active participation. I also thank our esteemed resource person, Dr. Sundrapandian sir, for spending his valuable time for the successfully completion of day 5 section. I once again thank our college management, principal, HOD, and my dear department faculty members. Thank you all.
Okay, thank you all. Bye.